Hey guys, I'm Pat Kelly. Okay, in this problem, they give us this function f of x, and what we're asked to do is to analyze and sketch the graph of this function, and they even specify to make sure that we label our relative extrema, our inflection points, and our asymptotes. This is familiar territory to you. What's new that we've been learning are these functions that involve an exponential expression. But remember the old sketch a graph type problems, you're familiar with the process of this. Okay, so bank on that. And what you'll see that's new is just when you get into your derivatives, we're going to have to know how to differentiate our exponential expressions. Okay? And of course, also, when we get into the algebra, which we always do, you're going to have to know how to solve equations involving those exponential functions. All right? So let me walk you through this one. All right, now right off the bat, I think I'm going to choose to rewrite the original function. Okay, this is my preference, but I really don't ever like a negative exponent within a fraction. So it usually looks a little bit neater to clean it up. And you don't have to do this. What I will do next is differentiate. And if you just went right ahead and differentiated from here, you'll get the same result I do. Okay? But I think mine's going to be a little bit easier, a little bit smoother in terms of the algebra. So if you like that kind of thing. So I'm going to do a rewrite. And as I said, just in terms of a rewrite, getting rid of that negative exponent. So we're looking at 1 over 2 minus 1 over e to the x. And that never looks good fraction within a fraction, so I'll get a common denominator here. It's not too hard. 2e to the x minus 1. My common denominator was e to the x. Now you can see the flip here is my last step. E to the x on top divided by 2e to the x minus 1. Okay, so the fruit of my labor there then is the original function equals this expression, no negative exponents, and the algebra I think is going to be a little bit friendlier for us as we proceed now. So now let's proceed. To find relative extrema, when I said that you're familiar with this, you know how to find relative extrema. You have to find critical points. To find critical points, you need the first derivative. So now we need f prime of x. And this is where I was rambling a little bit about. I rewrote, I'm going to differentiate from here. If you wanted to differentiate from here, I know you could do it. We'll get the same result at the end, okay? So I'm looking at this expression. If I'm going to differentiate that, that's a quotient rule, right? Overall a fraction. So now I'm going to do my quotient rule, which is the derivative of the top, bottom left alone, subtract, top left alone, and then the derivative of the bottom, which is 2e to the x minus 0. Okay. Quotient rule, so we got the big divided by, and then that bottom squared. 2e to the x minus 1 squared. Okay, now you might be thinking that doesn't look so friendly. I promised you friendly algebra, but take a closer look at it. When I go to distribute this e to the x, I'm going to have 2 times e to the x squared, or e to the 2x. And right here's the exact same thing. E to the x times 2e to the x, and they're opposite signs. So they subtract out. I promised. Easy, nice algebra. I always hate to say easy, but friendly is a good word. So those are going to be gone. I'd still have this e to the x distributing through to the second term within the parentheses. So my entire numerator is just minus e to the x. And that denominator, there's no simplifying that. If you thought to expand the parentheses, it usually doesn't do you any good in the denominator of a quotient rule. You're not wrong to, but the question is, what we're cleaning up here is, what are we going to do with it? Remember, we're looking for the relative extrema, so we need critical points. So the whole point in taking the derivative and cleaning it up is because now you have your expression to use to find the critical points. So my critical points come over here. CP for critical points And remember, critical points, there's actually two types. I always go over here and say type 1, and here type 2. Setup of your work might be a little bit different, but conceptually the same thing. There are two different types of critical points. Each of the types uses the first derivative. Type 1 is where the first derivative equals 0, which means for me in a fraction that the numerator equals 0. So I'm looking at minus e to the positive x. Where does that equal 0? And type 2 critical points is always where the first derivative does not exist, which in a fraction always means that the denominator equals 0. Okay, so I'm just going to grab that denominator, 2e to the x minus 1, parentheses squared, and ask myself where that equals 0. Okay, so here's the algebra I mentioned you need to know with our exponential expressions is how to solve equations like this. All right? Now, minus e raised to the x equaling 0. You need to be able to solve that for x. There's a couple different ways you might do this. I think the easier way to do this real quickly is if you think about what the graph of this looks like. E to the x. If I cover up the minus sign for a second. In fact, you know what? Throw the minus sign over the other side, right? Because there's a 0 over there. So if you think about the graph of e to the x, you really should know what that looks like. Just a real quick sketch is all you need. Exponential growth, right? And it hugs the x-axis way off to the left. And I'm drawing this because now you're asking what value of x would make that function equal to 0. In other words, where does it cross the x-axis? It doesn't. So my answer here for type 1 critical points is none. Did I mention there was another way to do this equation? In case you weren't thinking of the graph, there is. If you want me to tell you, give me 1 minute. I'm actually going to do it over here. Okay, so you can go back and do this first equation a different way if you wanted to. All right, so now I'm going to look for type 2 critical points, solving this equation. Okay, squared is obviously insignificant. If I square root the other side, I still get 0. So I'll do a couple steps in my head here. I'm also going to throw the 1 on the other side and even divide by 2. I don't think this algebra is too tough in order to see that's the equation we're looking to solve. Okay? And again, something you need to be able to solve. And this is what I was referring to with the first equation. If you weren't familiar with the graph, you'd still need to be able to solve this. How? The same way that I'll approach this problem. And this is in the realm of the new stuff that we've been learning lately. How do you solve when the variable is up in the exponent? And the answer is, take the natural log of both sides. So if I take the natural log of both sides of this equation, we're looking at that. And the reason we do that, take the natural log of each side step, is that then that variable which is up in the exponent comes out in front and becomes multiplication. It's one of our properties of logs. Which is really good. The x is out of the exponent, but even better, or maybe an added bonus, is now we're looking at the natural log of e. And you know what that is. That's 1. So we've actually just solved this equation. X equals natural log of a half. Okay. So just real quickly back to this one. When I said if you didn't know the graph, you could now take the natural log of each side. You'd get that same no answer result for our type 1 critical point. So we have one critical point, this result from our type 2 work. Remember what we're doing, we're always trying to keep our head on straight. We're looking for relative extrema. We know that where they can occur are at the critical points. We only have the one. Now in order to determine if there is a relative extremum there, we want to take this critical point and we put it into what's called the first derivative test, remember? That really just means, not that you need to remember the name of it, but you need to remember what to do. That means take all your critical points and put them onto the number line. So I only have this one critical point of the natural log of a half. And we do that for as many critical points as we have. We do that just because we're going to test the derivative to see if it's positive or negative on either side of the critical points. And that tells us whether the function, the original function, is increasing or decreasing. And then we'll know whether it's going up to a max or down to a min. So that means I now have to go to my first derivative and test these intervals. So you have to be able to figure out some number to the left and also to the right of natural log of a half. So you might want to grab a calculator and find the decimal approximation of this, just so you know where you're at. So I'm going to grab my calculator. And again, I'm only doing this to find out what the natural log of a half is, because I don't know it off the top of my head. This is approximately equal to a negative 0.69. Okay. And again, only doing that so that then I know if I'm going to test to the left of it, I've got to grab something less than negative 0.69. I guess like a negative 1. So let's test x equals negative 1. To test, I'm putting it into the first derivative. This is easier than you might think. If your inclination was to keep a hold on to that calculator, look at your first derivative. It's not too bad. The denominator is always positive, right? Denominator is always positive. The numerator, maybe I should even explain real quickly. I'm only concerned with positive or negativeness, so you don't care exactly what it equals. So you know it's always positive in the bottom. Look at the top. Ignore the negative for a second. E to the x, even if it helps, you can remember my little graph. E to the x is always positive. So that's always positive, and there's always this minus sign in front. So even without a calculator, I know that the result of this test is going to be that the first derivative is negative. Without even putting any more thought into it, anything I test to the right, like if I had chosen to test x equals anything to the right of negative 0.69, the same thought process prevails and we get a minus there as well. Negative derivative. Which means, switch colors here even to start thinking about the graph. The first derivative test tells us that the original function is decreasing on that interval and also decreasing on that interval. And never changes from increasing to decreasing or decreasing to increasing. Which means, back to what they had asked me to find, the relative extrema, there are none. Okay? There are no relative extrema. So all I have is this one critical point, but it goes down and then it goes down. Okay, I have no change. I'll write this as somewhat of an answer for now. In terms of my relative extrema, there are none. But I've got a few more pieces of the puzzle to find. Okay, and then I'll put it all together and try to go from there. Okay, at that point, I think I'm going to try to clear some space and come back and do the other 2 bullet points there. Okay, I'm back. Hope you got a little bit of a breather. This is a long problem. What we had just done was find the relative extrema. We found that there were none. Now we need to find the inflection points and the asymptotes. And I still have my first derivative written up here, which of course you know is significant moving on, because in order to find inflection points, you need the second derivative. So let's take that first derivative and differentiate it. F double prime of x equals, and I've got my quotient rule again. Derivative of the top is just minus e to the x. Bottom left alone, that's this whole thing, 2 e to the x minus 1 squared. Quotient rule, then I have subtraction of the top left alone. But if I leave the top alone, there's a minus sign there. Let's just make that addition then, right? Now the derivative of the bottom, I've got looks like a chain rule actually. So 2, leave what's inside alone. Drop it down a power to the 1 power, multiply by the derivative of what's inside, which is looking like just 2 e to the x. All right. That's the numerator of my quotient rule. Now I've got the big divided by, and I've got that entire denominator squared. So we have 2 e to the x minus 1 squared to the 4th power. Okay, that was the calculus, which wasn't too bad, just the quotient rule and also knowing our derivatives of exponentials. But now we have to do algebra, okay, and it's usually where the challenge is. You got to make sure you know your algebra. I love expressions like this. If you don't, let me try to talk you through how to see this expression and how to do the algebra. Because I'll argue that this is like pre-algebra or algebra 1, like 7th, 8th grade. Because all you really have in that numerator are 2 terms, right? 2 expressions separated by that addition. So I'm looking for common factors between those 2 terms. I see each of the terms has an e to the x. So in my next step, I'm going to factor out that e to the x. Still looking for common factors between the 2 terms. And that set of parentheses shows up in each term. So let's also factor out that 2 e to the x minus 1 to the lower power, if you remember that too, when you're pulling out common factors. So I can only pull out 1 power, which means I'm done with what I'm trying to factor out. Now let's see what's left over on the inside from that first term. That e to the x is gone. That minus sign is still there. Don't lose it. In the parentheses, I've only pulled 1 factor away, so there were 2. There's still 1 factor of that 2 e to the x minus 1. Okay, then I'm ready for my plus sign and look into the second term to see what's left over. Oh, the e to the x is gone. The first set of parentheses is gone. So I have this 2, and I have this second set of parentheses, 2 e to the x. Close and close square braces. So make sure that makes sense to you. And I was trying to tell you, it's really just basic algebra. So you know how to do the factoring out of simpler expressions. Don't let the more complicated expressions intimidate you. It's still the same thought process, okay? All right, let me pick back up where I left off here, though, because this is incomplete. I don't have a denominator. So let me get my big divided by, and then this parentheses, 2 e to the x minus 1 to the 4th. And now what you have is something you can actually cross out, where I have these parentheses and the same parentheses. So the 1 factor up top divides out with 1 of the factors in the bottom. So now there are 3 factors, okay? Okay, well, you know what? I don't want this to look confusing to you when you look back at your work. So in fact, that cross out that I just did, I'll switch colors here. So you want to know that there was that factor in the numerator and there were 4 factors in the denominator. So that's what we just did, okay? All right, now let's take this expression and clean it up a little bit. It might look a little bit unwieldy, but it's not too bad. This equals all that's left outside the square braces is e to the x. And inside the square braces, I'm actually ready to clean that up a little bit, so I'll switch to just regular parentheses. Because here I have minus 2 e to the x plus 4 e to the x. So that's going to be 4, take away 2, 2 e to the x. All right? And then minus a minus 1 will be plus 1. And it cleans up kind of nicely, I think. And then divide by this 2 to the ex minus 1, now to the 3 power. All right? Okay. This is good. Quick reality check. Where are we? That was our result for the second derivative. We do that because we're looking for the inflection points that they told us in the directions to find. So we use the second derivative to find inflection points. Let me get ready for that work here. Switch colors even. And we're looking for inflection points. And just like the whole process, we're hopefully used to this, but like with critical points, we are now looking for where the second derivative in this case equals 0, which is in this case for a fraction where the numerator equals 0, and also type 2 inflection points, just like critical points, where the second derivative doesn't exist, so in a fraction form where the denominator equals 0. So the algebra I have to set up for myself here is looking at that numerator e to the x. Where does that equal 0? The second factor in the numerator, 2e to the x plus 1. Where does that equal 0? And as I mentioned, type 2 inflection points, that's where the second derivative doesn't exist. So I also have one more consideration. Where does this denominator equal 0? So we have 2e to the x minus 1 to the 3 power. And where does that equal 0? Well, as always, it comes down to the algebra, right? So we'll solve each of these equations. These equations aren't too bad to solve either, though. If you take a look at this first one, if you remember the graph of e to the x, always above the x-axis, it'll never equal 0, so I get a none here. Again, if you don't remember the graph, you could do your ln of each side. You'll get the same result. Taking a look at the second equation, I'll just do a real quick little bit of algebra by taking that plus 1 and putting it on either side. So I got a negative, divide by 2. I said real quick algebra because I want you to see that here again is one of those equations where we're going to get a result of none, right? E to the x always positive. Or again, take the ln on both sides, same result. Okay, so finally then we have this equation to consider. So I have this quantity to the 3 power equaling 0, real quick cube root of each side, right? So I'm really just looking at 2 e to the x minus 1 equals 0. And now I might try to tap into your short-term memory, right? Short-term, because it wasn't that long ago. We already solved that. This was x equals the natural log of 1/2. Remember? Okay, and in fact, I'll throw this at you, as I hope you've maybe even picked up on this on your own, is that we solved that equation and got that same result when we were looking for type 2 critical points, where the first derivative doesn't exist. What I'm hoping you might have picked up on your own is that if it's a type 2 critical point, that means the first derivative doesn't exist. It's got to be a type 2 inflection point, right? If the first derivative doesn't exist, then the second derivative doesn't exist. Okay, so no real surprise there. Now what? We did this because these inflection points then, they asked me to find those in the problem, but they also tell me where the concavity of the function might change. That's the real definition of inflection points. This is still actually just a candidate for an inflection point. It's only called an inflection point if the function changes its concavity there. So let's find out if it does. To do that, we get to our familiar number line where we're plotting all of these results for the inflection point candidates. And I only have the one, natural log of 1/2. And we do that work because now we test the intervals, as many as you might have created, to see if the second derivative expression is positive or negative. Remember, you don't care exactly what it equals, just its positive or negativeness. So you might have to remember what this natural log of 1/2 approximately equals. I seem to remember this. We did it on the calculator. Negative 0.69, all right? Which I'm only doing so that I have some reference in terms of how far to the left do I need to go. Looks like it's going to work if I test even just x equals a -1 in terms of being in this left interval. And on the right interval, this is easier because I can test x equals 0, right? Anything to the right of -0.69. So, all right. Now I've got to figure each of these out in terms of the second derivative, plugging in those test values, and again, just worrying about whether it's positive or negative. All right, quick observation, similar to what I tried to do with the first derivative, is take a look at your numerator up here. E to the x is always positive, okay? The parentheses, e to the x is positive, multiplied by 2 is positive, plus 1 is positive. That numerator is always positive. So I'm really just worried about the sign of the denominator, which I can't conclude it's always going to be positive or negative. I got that pesky cube root there, or cube power. So I'll do a little bit of math in my head. You could grab a calculator if you want to, I suppose. Here's the easy one. If I said I'm going to do it in my head, test x equals 0. It's easy because e to the 0, you know that, that's 1. 2 minus 1 is positive. Cubed is positive. This ends up being positive over here. For my number lines, I usually use 2 plus signs, 2 minus signs to just make it look a little bit different from my first derivative tests, but not important. Now let's test that x equals negative 1. If I put that in here, I'm going to do it in my head again here, I think, because e to the negative 1, that's like e in the denominator. Hopefully you remember that e is approximately 2.187828, something like that. Bigger than 2. So you have a 2 up here, something bigger than 2 right below it, so that fraction ends up being smaller than 1. Subtract 1, you've gone negative, cubed, negative, so these are negative. All right, if you did it on a calculator, you might have beat me, but I had more fun. All right, I have my results now for the second derivative's sign, either of the intervals. And you remember that this means concave down, this means concave up. That's actually why I use the double pluses and double minuses. Looks happy or sad, I guess. And now then, I was saying that those candidates for the inflection points, this guy actually looks like it might be one, because there is a change in concavity in the original graph. Okay, well, if it's an inflection point, then I need to take that value, that natural log of a half, and plug it all the way into the original to find out what its y value is. I mean, if I'm going to answer this question, what's the inflection point or points of this problem? I found out where, that's the x value, but I also need the y value so that I have the ordered pair. Okay, so I'm looking for f of the natural log of 1/2, which you might say, hey Pat, why don't you just put that negative 0.69 in? But you'll see this actually isn't too bad. If I go to the original expression and try to put that natural log of 1/2 in for x, I'm looking at 1 divided by 2 subtract. Now e raised to that negative x power, I'm going to try to view that as 1 over e raised to the natural log of 1/2. Okay. And I like this because e raised to a natural log, that's one of our properties where they kind of cancel each other out. So you're only looking at the 1/2. 1 over 1/2, that reciprocates to 2. So 2 minus 2, that's a 0 in the denominator, big red flag. So this is an undefined here. Okay, so we did really good work in finding our inflection point candidates, and we did find one where there's a change in concavity, but then you have to follow through and find what should be its y-coordinate to see if it actually exists, and it doesn't in this case. So the concavity does change there, but it's not technically an inflection point because you don't have a point there. All right. And also, that segues well for me into this last thing I have to do, asymptotes. What are you talking about it segues well? We just found out that the original function has an undefined value at a specific x value. Where is it? A couple places for us. At that x value, the original function is undefined, which means vertical asymptote, right? So we actually just addressed this first aspect of the asymptotes as well by doing this work. That was kind of cool. So I'm going to write this, maybe even in yellow, is we just found a result, an answer, a vertical asymptote at x equals natural log of 1/2. Okay, just a little bit more to do. We're almost done, but now I'm going to use that asymptote when I go to do my graph and plot that vertical asymptote right here, negative 0.69, right? So I'll have that asymptote. And when I'm going to do my graph, I'm going to know that at that asymptote, I even change concavity. So we're almost done. Whew. All we have left are the other types of asymptotes that you should concern yourself with, which are the horizontal asymptotes, right? Do you remember how to find those? I'll give you a second to remember. You remember. It's limits, right? So let me come here and find some space here. I'm going to do the limit as x goes to a positive infinity of the original function. So I got to grab the original function. 1 over 2 minus e raised to the minus x. Okay. This actually isn't too bad as a limit. I'm going to try to talk through a little bit of the thought process. It's actually more thinking than writing anyway. But if I think through this, e raised to a negative power, of course, imagine that's like a little tiny fraction, 1 over e to the x. 1 over e to the x, as x goes to infinity, e to the x goes to infinity. So this expression, this part of it right here, let me just grab that part of it. That's like a 1 over infinity. In other words, 0, right? So 1/2 is my answer here. Okay. Also, you want to consider the limit as x goes to a negative infinity. In good old days, maybe those are always the same answer when we have friendly functions like polynomials and whatnot, but you got to follow through and do each of these two limits separately. You'll see we get two different answers this time. It's still the same original function, the expression. And my thought process is a little bit different, but still just thinking. E to the negative x, but I'm putting in a negative infinity. I'm intending toward a negative infinity, so negative negative is like a positive infinity, right? So e to the infinity is infinity. 2 minus that, well, that's a negative infinity, but it's huge. So 1 over huge always goes to 0, right? Okay, so two different answers, two different horizontal asymptotes. When the graph heads to the right, it's going to tend toward a y equals a half line. When the graph tends to the left, it's going to be a y equals 0 asymptote. Let's put it together and finally wrap this problem up, okay? So, my graph, I'm going to go ahead and draw my asymptotes. We had that vertical asymptote at x equals a negative 0.69-ish. We have two different horizontal asymptotes. Y equals a positive 1/2 when I'm headed that way, and y equals 0 as a horizontal asymptote, but only when I'm headed to the left. Okay. Now I'm pretty much ready to graph this. Just for sake of completeness, I said there were no relative extrema. There are also no inflection points. But I am going to keep an eye on that change in concavity when I go to do my graph right now. Okay. From our earlier work, we knew that it was always decreasing. So I know that when I come and draw on this asymptote way off to the left, I've got to be below it because I'm decreasing. And I'm going to head towards this asymptote. So I go like that. Still decreasing. So when I get to the other side of my vertical asymptote, I've got to be coming from above it if I'm decreasing, and I'm going to be heading out towards that y equals 1/2 line. So I go like that. And without even thinking, I actually followed through on my concavity. I concave down, and it switches at that natural log of 1/2 value. It's concave up. I think we did everything they asked us to do. We sketched the graph with all of those key components, and I feel really good about it. So I hope that helps you through with some of the other problems, okay? Give yourself a pat on the back after that one.